Welcome to BoostBusters Gas Exchange Handbook, and this time it's chapter 50, dealing by single cylinder four-stroke gas exchange processes. Before entering this very interesting subject, I'd like to state that some important parts which formerly were included in this course have been outsourced, and that's the thermodynamics and unsteady gas dynamics, which you can found in deeper details in chapter 20 and chapter 40. There is also another interesting sub-course which are related to this course, and that's about the four-stroke cylinder heads and how to do component tests on them. That could be found in chapter 60. And why is this? Well, this is obviously YouTube, and YouTube movies shouldn't be too long because then people could get sleepy. So in order to keep the courses as compact as possible, I decided to do this outsourcing. This will be long enough, I promise you. Single cylinder four-stroke gas exchange process is of course a simplification compared to a multi-cylinder four-stroke engine. But it's amazingly how much of the gas exchange theory which is actually present also in a single cylinder engine. I have divided this course in two different sub-areas. The first, which I normally start with, is internal gas exchange system. That's related to the cylinder head, the valves, the camshafts, and so on. All four-stroke engines do need an internal gas exchange system, so I guess that's a good starting point. Most of them also have an external gas exchange system, which is defined by the pipe network, which is connected to the air side, on the cool side, and also on the exhaust side, which would be the hot one. In many cases, the outer gas exchange system, when it has significant length on the ducting system, have a big impact on the gas exchange system, and the physics behind it is a little bit different. Here with pictures, it's a little bit simpler to describe what is the internal gas exchange system and what is the external gas exchange system. In the center of the picture, I hope that you could recognize something looking like a single cylinder four-stroke engine. We should recognize the piston, the cylinder liner, the cylinder head, where the cylinder head contains the cams operating the valves like this, simplified of course, porting on exhaust side, porting on inlet side, and this very nice spark plug. On the other side of the coin, we have the external system. The blue part will be the inlet primary pipe. The orange one would be the exhaust primary pipe. When it comes to the external pipe network on the single cylinder engine, especially on multi-cylinder engines, the pipe network on both air side and exhaust side becomes much more complex. We have air filters, we have air boxes, and we have other cylinders joining to the same plenum. And on the exhaust side, we have exhaust after treatment, silencers, and of course also other cylinders entering the same collector pipes and so on. But those challenges I like to save until we meet again in the multi-cylinder course. But from now on, we focus on the internal gas exchange system. A good starting point in my mind describing about the internal gas exchange system would be to present for you the valve lift event, which means that I will show you how the valve lift for intake and exhaust valve is changing while we're rotating the crankshaft, which is represented on the horizontal axle. So this would be crank angle rotation, this will be valve lifts in millimeter. The first curve here represents the exhaust cam valve lift, and exhaust cam displacement and valve lift could be a little bit different depending on how the system looks like. And to be stringent, I would prefer to stick to valve lift, then we don't do any mistakes here, or I don't do. Anyway, keep also in mind that all gas exchange processes starts with emptying the cylinder. So the exhaust period always comes before the inlet period. And this is something I use in my nomenclature so we don't mix the two sides together. After the exhaust cam have closed here, we start the inlet valve lift curve here. And at the end of the low pressure cycle, the gas exchange is finished by closing the inlet valve. In order to position the cam loops in a good way, we have something called loop center angle. This is loop center angle for the exhaust cam. This is the loop center position for the inlet cam. And describing where they are positioned, forward or backward, we use something called the loop center angle, in this case for the intake cam. And this would be the loop center angle for the exhaust cam. What is it mere to understand? Well, since it's a 4-stroke engine, we have a lot of top dead centers and bottom dead centers. This would be the bottom dead center for the expansion phase. This would be the top dead center, but not for firing. This is the gas exchange top dead center. And here we have the second bottom dead center, which could be called compression bottom dead center. The gas exchange could be divided in 5 to 6 different subgroups. The first one would be the exhaust blowdown period, which happens when the exhaust valve open and until we reach bottom dead center. From bottom dead center to top dead center, we have the support of the piston pushing exhaust gases out of the engine, and that period is called exhaust pumping. When we are slowly closing the exhaust valve before and starting actually opening the inlet valve a little bit earlier, we have the overlap period. When the overlap is done, we are moving from top dead center to bottom dead center with the piston, and this is inlet pumping period, where the piston takes some power from the crank to inhale into the engine. This happens to the bottom dead center for compression, but normally the inlet valve is open a little bit longer, and that period is called inlet ramming. Moving into this slide, I have changed the valve lift curves a little bit, as you can notice. I am focusing completely on the inlet period for reasons of simplicity, so the exhaust part, which was situated here, is no longer here. The second thing is that I have changed the dimension of the vertical axle from valve lift to valve area. The other stuff in this figure should be kept constant. So what valve area do we really have available for mass transportation through the poppet valve? Well, I think a good starting point would be to look into this picture, which is a picture of an inlet port and inlet valve. We recognize the poppet valve with the flat part here and the stem popping out here. The diameter of the valve is called dV, and for reason of simplicity we could imagine that this is the outer diameter of the inlet valve. In real more complicated life, the critical diameter for the flow is actually changing versus valve lift. But let's keep it simple for the time being. T would be the valve lift. And I think we could all sense that if we push the valve opening a little bit to a valve lift of T, having a diameter available named dV, we also create some level of circumference around the poppet valve. That circumference would most likely be good old P 3.14, as I guess you remember, multiplied with dV, that's the circumference. If you multiply that with T, you will have a curtain area, which would be a kind of annular area where flow coming from the port, coming down to the poppet valve, will vanish out in the combustion chamber more or less gradually. Well, if life would have been very uncomplicated, that would have been it. But unfortunately, life is complicated. And in this case, the complication is the bending of the port in the inlet port. So the ideal air coming straight from the atmosphere need to bend. We will have separation challenges with air not wanting to follow the inner radius. So to feed the curtain area will not be equally efficient all the way around the poppet valve. And how to take care of this? Okay, how do we perform taking the curvature of the inlet port or the exhaust port into account to be able to calculate the efficient area available for gas transportation? Well, we need to do some level of steady state component testing, or potentially three-dimensional CFD calculation will be able to do the same thing virtually. But if we start with the experimental way of doing things, what you do is to connect your cylinder head or the inlet duct to something very similar to a vacuum cleaner, able to keep the pressure ratio independent of time at a certain ratio. The pressure ratio could be something between 5 kPa differential pressure up to about 10 kPa. It depends a little bit on the purpose and who you're talking about. This way you could position the valve at different heights, and that's represented by the horizontal axle in this diagram. Here done not by absolute millimeters, but T, which is valve lift, divided by the outer diameter of the valve. When you position the valve at different heights, you are producing different mass rates. The measured experimental mass rate will be the most important part. Then you divide that with the theoretical expected mass rate using the pressure ratio you have in the test. That ratio of real mass rate and expected mass rate will create a constant called CF, which is a flow coefficient, and that is found on the vertical axle. If the duct or the port would be completely perfect, we will move on a diagonal in the diagram, and at peak valve lift approach a CF value of 1, which would indicate that the theoretical mass rate and the experimental mass rate would be the same. But because of the curvature in the port and the vicinity of the valve, which is blocking everything and making also complicated, the true CF curve versus valve lift would look like the blue curve and starting to bend down and reach a maximum level of, well, say 0.7. That depends on the status of the candle. We can also say that at lower specific values, it's the behavior and the geometry of the seat which controls the flow, while from about 10% of the valve lift, the port and the bending part becomes prominent. We can now expand the area expression to area seat efficient, which would be P, this 3.14 multiplied with dV, the diameter, and then multiplied with the valve lift. Here you have the geometrical area, and then multiplied with the CF coefficient, which comes from the flow test. We are now able to go into the valve area diagram again, and please note that it's now valve area efficient. So here we have brought in all the parameters impacting the available area, so we could say that we have a good expression of the area dimension. Here on the crank angle dimension, we are still fine, and mathematically we are now creating something called an integral, or a kind of summarization of what area we have available during the period. But because the area is changing by time or by crank angle, mathematically it becomes a little bit more complicated. Anyway, what we end up in is something called angel area. That would be the dimension of this, call it fictive area in the diagram. This angle area could be compared with the swept volume. And if you compare your available crank area by the swept volume, you get an indicator of how well suited your gas exchange system is to serve a certain swept volume. You can move one step further and introduce engine speed. If you do that into crank angle per swept volume, you end up in something a little bit more known to mankind, at least a little bit, called time area per swept volume. Time area per swept volume is actually a kind of inverted gas velocity. It's an incompressible average the gas velocity in a sub-period of the gas exchange. These figures could be utilized as a guidance in order to judge for a certain engine, for a certain engine speed, and maybe also power level, what size of the inlet valve, exhaust valves, valve lifts, and duration of the cams you would expect to be able to provide the best possible performance from the engine. Personally, I enjoy to invert the time area per swept volume. So instead of second per meter, I would achieve meter per second. And then you have a measure of this incompressible steady state average speed in the gas exchange event. But how you decide to do it is entirely up to you. Keep in mind that these figures are just estimates. They are not based on Navier-Stokes equations. It's just a first recommendation before entering simulations or engine testings in dyno. You could choose to stick to time area per swept volume. Personally, I prefer the inverted value, which is a kind of gas velocity which creates a better intuition in my mind. And you could then describe this velocity as something named incompressible averaged mean velocity. And for a four-stroke engine, you could find 6 different mean velocities, and I would describe them. Coming back to the valve lift event like this, it starts with exhaust blowdown in compressible average mean velocity. This is in great control of pumping losses in the engine. The next one would be the exhaust pumping in compressible average mean velocity, which is active when the piston is pushing out the exhaust gases. There are two different overlap mean velocities. Is the one related to exhaust, which is exhaust incompressible average mean velocity, and it's the inlet overlap incompressible average mean velocity. These are especially important when you're working with highly tuned engine, where the valve overlap is very important to improve scavenging efficiency and volumetric efficiency. Next out is the inlet pumping incompressible average mean velocity, active during the high valve lift for the inlet side when the piston is drawing air into the engine. The last one would be the inlet ramming incompressible average mean velocity. It's now time to have a look into the external gas exchange system of the single cylinder 4-stroke engine, as sketched here on the slide. So it's the air side and the inlet primary pipe and the exhaust primary pipe. For you who have been looking on the chapter regarding gas dynamics, you recognize this picture. This is a picture of a so-called physical plane from compressible flow, where you can sketch the engine and the exhaust primary pipe on a horizontal axle, which is distance. On the vertical axle, we basically have a time domain, but you can convert the time domain to crank angle if you just decide at what engine speed it should be a true statement. So here we have the exhaust period and the intake period sketched in this diagram for 6,000 RPM. At 4,000 RPM we do it again, but because of lower engine speed, the time spent for a certain duration in crank angle will be bigger. What's happening now when the exhaust valve opens is that the high pressure inside the cylinder will propagate out in terms of a compression wave. The wave pattern here is simplified. Normally they take a little bit of a time, but in this case they are thin lines, just to make it a little bit easier to understand each individual pressure wave contribution. As you remember from the gas dynamic course, a compression wave hitting open end or partly open end will reflect back with changed identity as a decompression wave. And when pressure waves like here and here passes a certain particles, the particles are given additional speed in a direction which could either be in the direction of the pressure wave propagation or in the other direction, depending on the identity of the pressure wave. Ideally, we like the decompression wave to come back to the engine during valve overlap, which obviously happens at 6,000 RPM. This end of the engine would be felt like a slightly closed end, so the decompression wave will reflect back out to the atmosphere, change identity and direction again, and come back into the engine. At 6,000 RPM, exhaust valve is already closed, doesn't matter, no impact on the gas exchange, but at 4,000 RPM, this compression wave could actually hurt the engine in the valve overlap before the exhaust valve is closing. And instead of improving the volumetric efficiency, which is what's happened at 6,000, the other way around could happen. So we push exhaust gases into the engine again, and we could have a little bit of a valley in the torque curve or volumetric efficiency curve, sometimes referred to as megaphonitis, especially if you have big valve overlaps. Also note that the inclination of this line is actually showing the speed, the propagation velocity for the pressure waves, and the CG is the velocity for the mass rate. And here you could see the big differences in velocity. So the gas particle and the mass rate is much, much lower than the propagation speed of the pressure waves. Now we know a little bit about the mechanics in the exhaust primary cycle. Here is two different pressure traces taken very close to the exhaust valve, but downstream the exhaust valve. These type of diagrams will show the pressure history, and this is happening versus crank angle rotation, which was the vertical dimension in the last diagram. At bottom dead center, the pressure wave is peaking, the pressure wave which is the outgoing compression wave when the exhaust valve opens. We can see that the pressure drops down here, and we have a minimum a little bit before 360 degrees, which is the gas exchange top dead center. If we move to the other picture, it's very similar, but the difference is that we do have a little bit of a higher pressure amplitude, but most important, the deepest valley in the pressure traces is happening right over the top dead center for gas exchange, where we have the overlap. The difference between these two curves is because of different length of the exhaust primary pipe. This is an 800 millimeter pipe. This is a 300 millimeter exhaust pipe. The 300 millimeter exhaust primary pipe will be a little bit too short to really support the engine gas exchange wise at this engine speed, while the 800 millimeter longer pipes actually do. Another thing we could notice in the diagram is that we have not only one pressure trace, we have three. The red one is the total pressure, or the superposition pressure, which is the sum of all existing pressure waves at this point in time. Colors are a little bit bad here, but the yellow one, the yellow pressure trace, is the backward moving or incoming pressure waves, and what seems to be a bit bluish for me would be the forward pressure waves going out in the exhaust pipe. This could only be obtained by simulations, since experimentally achieved pressure waves are only the total one. And the important message from this is that simulations are very, very important to be able to understand what is a right and what is a left moving pressure wave. If you don't know that, you don't know anything about how the particles or the mass rate is influenced by the pressure waves. Test-driven results from a pressure transducer cannot help you in that respect, but tests are still very important, because having the superposition pressure from both simulation and experiments, you can compare, calibrate, and get much more out of your simulation model. On the intake side, we also have a primary pipe cycle, of course an inlet primary pipe cycle. You recognize yourself, I think, from the other slide. We have the inlet primary pipe, cylinder, piston, and valve here, and the vertical one would be the time domain specified for a given engine speed, 6,000 RPM, to crank angle. What's happening when the inlet valve is opening here, the blue line, is that a decompression wave is generated, moving out to the open boundary at the ambient, changing the identity, coming back to the engine as a compression wave. Since this is the last thing happening in the low pressure cycle or the gas exchange, this compression wave could actually boost the engine and mimic a steady state boost pressure of about 20 kPa or something. Higher order pressure waves on air side is very rare because the amplitude of the pressure waves on the air side is much lower than on the exhaust side. So therefore, this diagram is a little bit short. What could also be added is that the generation of the decompression wave, which I have sketched now from just the product of the descending piston and the displacement activity creating a pressure ratio over the inlet valve. But in more highly tuned engine with larger valve overlap and an ongoing exhaust primary pipe cycle, we will also have some influence and support from the exhaust side, where very high amplitude decompression waves could join, also going right through the engine to the air side, which is of course improving the peak volumetric efficiency to some degree. My intent now is to show some examples from a single cylinder 4-stroke engine at about 500 cc and 30-35 horsepower. Here in the first slide, you could repeat what you learned from the thermodynamic course in terms of the specific mean effective pressure. And we remember indicated mean effective pressure, brake mean effective pressure, friction mean effective pressure, and pumping mean effective pressure. And here you could see for a naturally well-behaving engine what levels you could expect. Let's start out with the gas exchange exercise, which is very simple to do, especially if you have a double overhead camshaft engine with separate cams. This is a cam facing event on the intake side. The lube center angles, the definition is already presented, could be showed like this. The first figure 100 is the lube center angle for the exhaust valve. The exhaust valve would be this if you look in this diagram. The second one, which is currently 115, would be the lube center angle for the intake valves. So as you can see in this example, exhaust valve is fixed and we are trying out 3 different lube center positions for the inlet valve. What normally happens then in a volumetric or delivery ratio diagram versus engine speed is that we could change the behavior of the delivery ratio curve, and when we push the intake cam towards earlier phasing, that will be lower numbers, we will most likely increase the volumetric efficiency at lower engine speed. And this is because we are managing around with the time areas per swept volume. Cam facing on the exhaust side is the other way around, of course. We freeze the inlet cam facing and we just change the facing of the exhaust cam. Normally, but not always, what we obtain with facing the exhaust cam is impact on the pumping mean effective pressure. So the earlier we go with exhaust valve, the easier it is for the engine to pump out exhaust gases, so we don't need to take away too much power from the piston doing the work for us. Also in this case, when we do cam facing, what we actually are doing is playing around with the time area per swept volume, or if you like it, incompressible average mean velocities in the internal gas exchange system. The last 2 examples is happening on the external gas exchange system. The first activities is to change the length of the exhaust primary pipe. We did see some pressure traces from this, but we didn't see the impact on how the engine performance would look like. Still, delivery ratio, volumetric efficiency versus engine speed. The starting point, if you like it, would be the short exhaust primary pipe from the former example with the pressure traces. 300 millimeter will generate the dark blue volumetric efficiency curve. Increasing the length to 800 millimeter, we will obtain something like that. And around 6,000 RPM generate the appreciated decompression wave in valve overlap, improving the volumetric efficiency. Now jumping over to intake side. Here we are changing the length of the inlet primary pipe instead. This is also the delivery ratio versus engine speed, and we can see that the short intake pipe is generating a volumetric efficiency peak around 5,000 RPM. Increasing that length to 600 millimeter, we have the magenta curve, and we have the peak volumetric efficiency around at 3,500 RPM. On our side, it's easy to make variable intake length manifold, and this is how some of those systems is operated. Latest but not least, for you who want to study more details, of course, I recommend my own book, which can be purchased at www.jure.com if you want it in paper format. And when you're having questions, don't hesitate to call me at Lennarth at BoostBusters.com. Thank you very much for attending this presentation, and take care.